In this video, I would like to solve the three problems that deal with empirical formula. So make sure that you have time to watch the video. So the first problem will just be a normal empirical formula problem. The example is shown here. The second problem will involve empirical formula when a substance is undergoing combustion. So for example, we have a hydrocarbon, a compound that has carbon and hydrogen only, and this hydrocarbon is undergoing combustion reaction, and the products are going to give carbon dioxide and water. The third problem will be a combustion reaction, but now this one involves carbon, hydrogen, and oxygen. We can also replace nitrogen for oxygen, but in this case we will deal with oxygen. So first things first, let us look at this problem. First, let me get a pen. So in this example, we have a compound that is 43.7% of phosphorus and 56.3% of oxygen by mass. What is the empirical formula of this compound? So before we go on to answer the question, let us take note of the percentages given. And remember, in class we said that when given percentages you need to change them to mass. So let's see how this works. So how I will arrange a problem like this one, I will arrange the two elements, phosphorus and oxygen, the two elements found in our empirical formula. Then I'll give each one its percentage. So phosphorus is 43.7%, oxygen is 56.3%. So the second thing I will do is to change the percentages to mass. So the magnitude or the number is the same, we just remove the percentage. So in terms of mass, in grams, 43.7% changes to 43.7 grams. So this will be our mass. And 56.3% changes to 56.3 grams. So now that we have the mass, we know the mass of phosphorus in the formula and we know the mass of oxygen in the formula. Now that we have the mass, we can calculate the number of moles. And we know that number of moles is given by this mass divide by the molar mass of phosphorus. And the molar mass of phosphorus is it should be about 30 something or 30 point something. So when we divide by that, this is what we get. So the mass of phosphorus here divide by the molar mass of phosphorus. That gives us 1.41 mole of phosphorus in this compound. We do the same thing for oxygen. The mass of oxygen divide by the molar mass of oxygen. This gives us 3.542 mole. So from the mass we are given, we know that we have these moles, 1.41 for phosphorus and 3.52 mole for oxygen. Now, once we get the number of moles, we need to divide by the smallest number of moles, because we want to obtain the smallest ratio of the moles. So we look at this. We see here we have 1.41 mole. Here we have 3.52 mole. So in this case, the smallest number of moles is 1.41 mole. So we are going to divide the moles of phosphorus and the moles of oxygen by 1.41 mole and see what we are going to get. So 1.41 mole divided by 1.41 mole gives us 1. 3.52 mole divided by 1.51 mole gives us 2.50. So the next step is to write this in this type of fraction, or write it in a form of an improper fraction. So here what we are going to do is to turn the decimal, like in this case, to improper fraction. So 1 remains 1, but 2.5 becomes 5/2. Now the next step is to get rid of these 2 so that we don't have fraction, we have whole number ratios. So we do that by multiplying both sides by this denominator. So I am going to multiply this by 2 and also multiply this one by 2. In that case, I get rid of the 2 down here to get this answer. So for every 2 phosphorus, I have 5 oxygen, which means my formula should be P2 and O5. This is the empirical formula, that is P2 and O5. This is obtained from the by changing the percentage to mass and then calculating the number of moles and then dividing by the smallest number of moles and then changing the fraction to improper fraction and calculating or removing the denominator by multiplying with the denominator, multiplying both sides to get 2 and 5, and then we say we have 2 phosphorus and 5 oxygen. So this is empirical formula problem number 1. Now once we know this empirical formula shown here, we can also calculate the molecular formula. especially if you are given the molar mass of the compound. So that is the next example that we are going to talk about. So we are saying if the compound in the previous question has a molar mass of 2.88 grams per mole, what is its molecular formula? So how do we solve that? To solve that, we need first to find the empirical mass. That is, add the masses, 2 phosphorus, the mass of 2 phosphorus plus the mass of 5 oxygen. That gives us the empirical mass, that is mass of the empirical formula. Now the second step is to divide the molecular formula by the empirical formula to obtain a number. So in this case, we have the molar mass divided by the empirical formula, and it gives us 2. So what do we do with this 2? The 2 here indicates that the empirical formula should be multiplied by 2 to obtain the molecular formula. So what you are going to do is to multiply these numbers here by 2. So in this case, we multiply the 2 times this 2, and then multiply the 5 here times 2 to give us P4 or 10. So this is the molecular formula of the compound. So that covers our empirical formula problem. Now this is the simpler empirical formula problem. In some cases, you will not be given the percentages. What you can be given is the amount of carbon dioxide and water produced from a certain compound, and you may be asked to determine the empirical formula of that compound. That is our next example. So let's look at this example. So upon combustion, a compound containing only carbon and hydrogen produces 1.83 grams of carbon dioxide and 0.901 grams of water. Find the empirical formula of the compound. How do we solve this problem? First, you need to determine the original molecular formula of that compound. You can just give it letters because we don't yet know the numbers. But we know that the compound contains only carbon and hydrogen, but we don't know how many carbon atoms are in that compound. We don't know how many hydrogen atoms are in that compound. So the first formula that we are going to write is CX and HY. So X is the number of carbon atoms, while Y is the number of hydrogen atoms. This just tells us that our compound is going to have carbon and hydrogen. The next step is to determine the mass of carbon. Now, where do you get the mass of carbon? To find the mass of carbon, you need to look at this. carbon dioxide is the compound that contains the element carbon here. Now, what you want to do is to isolate carbon from carbon dioxide. So to do that, you need to determine a conversion factor, something that can convert this mass of carbon dioxide to the mass of carbon. And what is this conversion factor? So conversion factor is just the ratio of carbon, or the ratio of the mass of carbon to the mass of carbon dioxide. That is our conversion factor. What is our given quantity? This is our given quantity. So to get the mass of carbon, we need to multiply this mass times the conversion factor, as we can see from here. So I will multiply 1.83 grams of carbon dioxide times the molar mass of carbon divided by the molar mass of carbon dioxide. And this gives me the mass of carbon as 0.499 grams. I do the same thing for hydrogen. Hydrogen is present in water. And from the problem, we see that we have 0.901 grams of water. Another thing that also you need to think about is that water has 2 hydrogen atoms. So we need to take note of that. Now, how do we determine the mass of hydrogen in water? We also use a conversion factor. So in this case, our conversion factor is the mass of 2 hydrogen atoms divided by the molar mass of water. So what you need to do is to multiply this given quantity times that conversion factor as shown here. So this is the given quantity, the mass of water, times this is the mass of 2 hydrogen, the mass of 2 hydrogen atoms, divided by the molar mass of water, and that gives us this mass. So based on this, we can say that the original compound had 0.499 grams of carbon and 0.1008 grams of hydrogen. That's what we have. Now the next step will be to determine the number of moles for both. And we know that the number of moles are found by dividing the mass, the given mass, by the molar mass. So in this case, for this situation, our given mass is 0.499. This one we divide with the molar mass of carbon, which is 12.011. We do the same thing with hydrogen here. We divide the given mass here, 0.1008, divide by the molar mass of one hydrogen atom, the molar mass of hydrogen, which is 1.008. So this will give us the number of moles. After obtaining the number of moles, we see that we have 0.0415 of carbon and 0.1 moles of hydrogen. Now, the next step is to divide by the smallest number of moles to obtain the smallest ratio. So this one is the smallest number of moles because 0.0415 is bigger, or 0.0415 is smaller than 0.1. So we are going to divide both of them by 0.0415. This is what we get. So when we divide this, the answer is 1. That is for carbon. So for every 1 carbon, there are 2.4 hydrogen. But 2.4 is similar to 2 and 250. We can change this to improper fraction, that is 12 over 5. Now, once we get 12 over 5, we want to get rid of this 5 here. So you need to multiply both sides by 5. So I multiply here by 5 and I also multiply here by 5. In the end, this cancels with this one. So what I'm saying is, for every 5 carbon, there is 12 hydrogen. And this gives us our empirical formula, C5H12. So as a reminder, this one is when we are given a compound that contains only carbon and hydrogen, and this compound produces carbon dioxide and water. Now let's move on to the next compound. Now this compound contains carbon, hydrogen and oxygen, but we are going to use a similar procedure with only a single difference. So let's focus on that one. Upon combustion, a 0.8233 gram sample of a compound containing only carbon, hydrogen and oxygen produces 2.445 grams of carbon dioxide and 0.6003 grams of water. Find the empirical formula of the compound. So for this problem, you also need to find the original molecule, the formula of the original molecule. Now using X, Y and Z, because we have 3 elements in that molecule. So we have CX, HY and OZ. The second part is to determine the number of carbon in carbon dioxide. So we use the same formula like the previous problem and use the same conversion factor. So what we are going to do is just multiply this mass of carbon dioxide by the conversion factor to give us the mass of carbon. So after multiplying, we see that in this compound we had 0.667 grams of carbon. We do the same thing with hydrogen, the hydrogen found in water. The same conversion factor like we used previously, but this is the mass where we are going to obtain the mass of hydrogen. So 0.6003 grams of water times the conversion factor, that is the mass for 2 grams of, or for 2 hydrogen atoms, divided by the molar mass of water. So in this case, we see that we have 0.0672 grams of hydrogen. Now we get the masses: the mass of hydrogen, the mass of carbon. But we don't know the mass of oxygen. So how do we obtain the mass of oxygen? We know that the original mass of the compound is 0.8233 grams. But from this original compound, we need to remove the mass of carbon, which is 0.667 grams, and also remove the mass of hydrogen, which is 0.0672 grams. The remaining mass here will be the mass of oxygen. So this is what we are demonstrating here: the total mass minus the combined mass of carbon and hydrogen. So based on this, we see that we have 0.0891 grams of oxygen. Now we have the masses. What we need to do is to find the number of moles. So like we did with the previous problem, you need to divide the moles here, 0.667 divided by 12.011. It gives you the mole. Mass over the molar mass of carbon. We do the same thing with hydrogen here, 0.0672 divided by 1.008. So we get the number of moles of hydrogen. For oxygen, 0.0891 divided by 16. So that gives us the number of moles of oxygen. So this is how the number of moles will look like. We are going to have 0.0555 of carbon, 0.0667 of hydrogen, and 0.00557 of oxygen. The next step is to divide by the smallest number of moles to obtain the smallest ratio. In this case, this is our smallest number of moles. So we are going to divide all these by this number of moles. Now, how will it go? This is what we are going to have. For carbon, we are going to have 9.96. For hydrogen, we are going to have 11.7. For oxygen, we are going to have 1. So we can say that our compound has C10, H12, and O1. That is, our empirical formula is going to be C10, H12, and O, just O. That's how we solve these empirical formula problems. Make sure to study them. Make sure to practice with other problems in your book and the problems that I gave you in class. Thank you.